Applying L'Hopital's rule when we know the definition of a function is as simple as taking derivatives. But what if you don't know the actual definition for a function and you only know some function and function's derivative values? Well, we have a table of values here. We know when x is -7, -5, -3, what the values of f and what the values of the derivative of f are. We can read those straight from the table. So we're going to apply this L'Hopital's process to the limit x approaches -3 for f, this mystery function, evaluated at 2x minus 1 divided by x squared minus 9. So notice we have a composition of functions in the numerator. We know that x is approaching -3, which means 2x minus 1 is turning into -7. So our numerator is going to look like f of -7, and we can read that from the table. The middle row and the second column, f at -7, is 0. Our denominator, x squared minus 9, evaluated at x equals -3, gives us a 0, which means our limit, in fact, does take on the indeterminate form, 0 over 0, perfect for applying L'Hopital's rule. We apply L'Hopital's rule, which differentiates the numerator and the denominator of our rational function separately. Looking at the derivatives here, we do need the chain rule for the numerator because we're looking at a composition of functions. Since we don't know what f is, we don't know the definition of f, we do know that we're going to have the derivative of f, so f prime, with 2x minus 1 still plugged in, and we need to multiply that by the derivative of that inner function from the composition. So we need to differentiate 2x minus 1 and multiply it to the f prime at 2x minus 1. So finally we see that our L'Hopital's rule sends us over to the limit of f prime, evaluated at 2x minus 1 times 2, divided by 2x. We can divide off the common factor of 2 so that our limit's a little simpler. Now we know what happens to 2x minus 1 when x is approaching -3, so we're really just looking at f prime at -7 divided by -3. That simplifies to give us -2. So in this case we applied L'Hopital's rule, but with a little less algebra because we didn't know what f had a definition of. We only knew f at certain points, and luckily we had all the points we needed to finish this problem. Let's try another one. Similar idea. Here we've got a table of values, the same table, but we're looking at a different limit. We're going to start by saying what happens to our numerator and denominator when x is approaching -5. So in the numerator I have a composition of functions. The innermost function is f of x. So when x is -5, f of x becomes f at -5, which we can read from the table. So middle row, third column, f at -5 is -3. But that goes back into f again. So f of f, that's like f tucked into f, is going to be f of f at -5, which is f at -3. So we're just cleaning up the inside function. We know that turns into -3, and reading from our table, f at -3 is 0. So our numerator is heading to 0 when x is going to -5. Let's look at our denominator. 3x plus 15 when x goes to -5 goes to 0. So our rational function does have an indeterminate form of 0 over 0 when x is approaching -5. We can apply L'Hopital's rule because we have the appropriate indeterminate form. So taking the derivative of the top, derivative of the bottom, we see we're going to need the chain rule in the numerator. Our chain rule is going to say the derivative of the outside function, f, with the inside function plugged in untouched, so f prime evaluated at f, but then multiplied by the derivative of our inside function, which is f. So we're multiplying by f prime. So we have f prime at f times f prime at x. And in our denominator we have a constant, which we like. That's one of our favorite parts of applying L'Hopital's rule. We have 3 in the denominator, so no potential for an indeterminate form here. We already calculated what happens to f when x is approaching -5, so we can rewrite this as f prime at -3 times f prime at -5. So we replaced f of x with -3, but we replaced x with -5. And then we can read from the table what f prime at -3 is. F prime at -3 is 9. We also need to read what f prime at -5 is. F prime at -5 is -1, so our numerator becomes 9 times -1. And all of that's divided by 3, so this simplifies to be -2. So we have two examples here of applying L'Hopital's rule in a case where we don't know the definition of the function inside of our limit. Let's take a look at one other version of this type of question. Here we're given a graph. We're not given a table of values, but we will do this basically the same way. Our limit is approaching, x is approaching 4, and our function is g of x minus 3 divided by x squared minus 2x minus 8. We don't know what g is, but we can see a graph of g. And because this is a pretty simple graph, we can read what g is equal to at given points, but we can also read the rate of change at g. We know that L'Hopital is going to have us take the derivative of that numerator function, so we're going to need to know what g prime looks like. So let's go through it just like we did the last ones, starting with looking at what's going on with our rational function when x is approaching 4. The innermost part of the numerator, x minus 3, that is turning into 1 when x approaches 4, which means we can read from the graph that g at 1 is equal to 0. So our numerator is going to turn into 0 when x approaches 4. Looking at the denominator, when x is approaching 4, that also goes to 0. So we do have an indeterminate form when x is approaching 4. We can apply L'Hopital's rule, taking the derivative of the top and the bottom. We need the chain rule in the numerator because g has a function plugged inside of it, so we take the derivative of g with the inside function still there. And if we take the derivative of the inside function, x minus 3, that derivative is just 1, so we don't have to show that. If you want to, you can write g prime of x minus 3 times 1. Or you can leave it off, because multiplying by 1 doesn't change anything. We do know that when x is approaching 4, x minus 3 turns into 1, so we're going to replace that with 1. So g prime at 1 in the numerator. Denominator 2x minus 2 becomes 2 times 4 minus 2. And this is where we need to read the graph to figure out what g prime looks like near x equals 1. Because g is this piecewise function with straight line segments, we can just read the slope of the portion of the curve where g at 1 happens. So we're going to read the slope. It goes up 1 over 2. Slope is rise over run, so g prime at 1 is 1/2. Now, the fact that we're saying g prime at 1 is 1/2 is true, but it would also be true at 0, at 2, at 1.5, at 2.5, over that entire segment where we just read the slope. The derivative of g is 1/2 along that entire segment. But we only care about what happens exactly at 1, so that's why we're writing g prime at 1 equals 1/2. Plugging that into our limit from L'Hopital, we get 1/2 on top, 8 minus 2 on bottom. That's the same thing as 1/2 divided by 6, which turns into 1/2 times 1 over 6, which is 1/12. And so that would be how we evaluate a limit with L'Hopital's rule when all we have is an image of the function.